Well, good evening and welcome to Space Oddities. Thank you very much for joining us on this Tuesday evening. We hope everybody out there is well. Joined this evening by the usual suspects, really. So let's just stop hogging the screen to myself. There we are. We can see them better now. So I'd like to say good evening to Keith. How are you, Keith?
I'm fine, thanks. Yeah, not done much astronomy, I'm afraid, this last week, but there you go. Yeah,
No, well, that happens.
yeah,
And we've also got Michael
mainly.
joining us. And Daz, of course,
Yeah, back from me travels,
back from your travels.
internet.
Yeah.
So I thought
So,
I'd spend it here.
yeah.
So,
So, I'd like to apologise in advance. We won't be having a viewers gallery nor a night sky guide tonight because Rachel couldn't join us because poor little Isaac has been quite ill with a chest infection, so she's looking after him. And Roger is MIA, so we don't know exactly where Roger is, but we hope he's okay. And we've got on a packed show tonight. Keith has joined us for the fourth part of his wonderful series about astrometry, mapping the heavens. So we're looking forward to that. And we've also got a couple of other things lined up for you this evening. We'd like to thank everybody who joined Daz and Michael for the live coverage of the Starship flight last week. The so-called IFT3, which stands for Integrated Flight Test 3. Thanks to everybody who joined the live coverage. Apologies that there was an abrupt end to it because we had technical problems our end. And so if you were watching it ended suddenly, sorry about that. But it doesn't matter because we covered the flight itself, and what an amazing flight it was too. We're going to be talking about that on today's show, quite obviously, because it was a momentous milestone in the development of SpaceX's Starship. And ignore the naysayers. It was an unbelievable success, even though it didn't end as one would have liked, or as I'm sure SpaceX would have liked. However, we'll talk about that a little later. Thank you to those of you who've bought coffees. A big thank you to Gerard for the super chat last week. We'd only just activated that feature, so thank you very much, Gerard, if you're watching.
Gerard's just done another super chat. Thank you, Gerard.
Hey. Oh, we have another, do we? Oh, hang on.
Yeah,
I need
thank you, Gerard.
to have a look and see. So Gerard, thank you so much. You are so generous, sir. We do appreciate it.
Yeah.
It all goes to keeping us, keep the ball rolling, keeping us on the road. So thank you so much. We do appreciate it. And if you would like to buy a super chat, you just click the icon that you'll see underneath the video. And the super chat really is for if you want to make a comment that you want to see highlighted so that people notice it, you can donate a sum of money to pay for that to happen. But obviously, we do accept donations in terms of coffee. And to that end, let me just put the link up for this. 1 second. Let me get my mouse to work. I've got a new mouse and it's I'm running it in. It doesn't appear totally happy at the moment. However, if you would like to buy us a coffee, that's the QR code to scan. If you look in the chat, you will also see a link for the same thing in the chat that should have just appeared. So thank you to everybody who regularly and not so regularly buy us coffees, because it is much, much appreciated. Don't forget that we have the Space Oddities merchandise. We have the T-shirt in a range of 10 colors with the Space Oddities design on the front. There's the QR code to scan. And again, the link should have appeared in the chat as well. It's also in the description of this video on YouTube. And these are really nice quality T-shirts. They retail for £20, which does include UK postage and packing. We've also got the Space Oddities hoodie available. This is in two designs: the zipper design with the Space Oddities design on the back, and the over-the-head design with the Space Oddities thing on the front. We've also got a variation of the T-shirt where the Space Oddities design is on the lapel position. And again, this is £20, including UK postage and packing. The hoodies, by the way, are £40, including UK postage and packing. And if you're ordering from abroad, please add £10 to the total value of your order to cover postage and packing abroad. So also, please don't forget to like this video, and please subscribe if you haven't subscribed. That's very important to help us on the road to greatness. So please like and subscribe. And if you can, leave a comment in the video when it's on YouTube, because that helps us get noticed by the YouTube algorithm. So thank you, everybody, for your support, as always. So in due to the fact that we don't have a gallery or a night sky for you this evening, back next week, of course. So if you have sent in your images, they will be featured next week. Don't forget that if you do wish to send a sky image into us, and it doesn't have to be deep sky or planets or anything, if there's a nice skyscape that you have with something interesting in the sky, that would be great as well. Mail them to spaceoddities@gmail.com. One image per email, please. And if you could just somewhere in the title include the word gallery, then that will help the auto thing pick it up and put it in the right place so that we don't forget about it. So there we are. So last week we had the test of the Starship vehicle from SpaceX. As you may know, this was the third attempt to get the Starship into orbit. This time around, though, they had a slightly different plan, because they decided not to try to get it into orbit so that it went around the Earth, obviously. It was put on a suborbital trajectory. Why did they do this? Because as it's such an early test phase of development, really, they didn't want the Starship to get into orbit and then it not coming down and be stuck floating about as a piece of space debris in orbit. So they decided to put it on a suborbital trajectory and splash down in the Indian Ocean. That didn't go to plan. Let's have a look at exactly what happened during this incredible flight. And first of all, we had a perfect liftoff and ascent. And I've got a short video here which squashes the whole mission into 2 minutes. There's no sound on this video, by the way, so sit back and watch a condensed version of IFT3 that took place on the 14th of March. So everything went well on the ground. Starship fired all of its 33 engines successfully. It's the second time that they've been able to do that. This is the view on the way up. This is the view looking down the spacecraft. And coming up very shortly, we had the separation phase, the so-called hot staging and separation of the booster from Starship. The booster drops away. You can see it disappearing off there on its descent back to Earth. Starship continued on its trajectory. And from then on, everything appeared to be okay. It went into a coast phase, which lasted about 40 minutes. Some fantastic views from the booster on the left and Starship on the right there. And amazing views of the Earth. You can see Starship. Don't worry, this is completely speeded up. This was the descent of the booster. The booster was lost, unfortunately, broke up at an altitude quite low to the ground of about 540 meters above the ground. We'll talk about exactly why that happened in a little while. There you see Starship venting the excess liquid oxygen that they put in the spacecraft only for weight to simulate a payload. And once it was up, it didn't need it anymore, so it was vented. At this point, as you can see, the Starship appeared to lose attitude control and went into a spin. And then, we saw this and we knew that there was a problem here, as you can see. But these views of the Earth are quite amazing. You can see the fins on the Starship trying to control that roll, but eventually they managed to get it facing bottom end down, re-entering through the atmosphere. You can see the plasma starting to surround the spacecraft. This was an amazing thing to get those pictures back. And then the Starship broke up at a few hundred miles above a couple of hundred miles above the Earth, they think. So that was the flight of the Starship. And I'd just like to go through some of the things that were good about that mission, some of the problems that actually happened. So this was the timeline. As far as I can make out, this was the timeline. I'm sure Daz or Michael will correct me if I have any of this wrong, but this is the timeline for the mission I've been able to piece together. Launch and ascent, all the 33 Raptors fired. The hot staging was successful. The separation of the Starship was perfectly successful, overcoming the problems they had with IFT-2. And then the Super Heavy did perform the so-called boost back maneuver, where it flips over and then goes bottom down towards the Earth, and then started its descent. Starship continued its ascent with all 6 Raptor engines functioning perfectly. The booster then starts to lose attitude control, goes into an uncontrolled roll, possibly a result of a failure with its grid fins, which are there to control its trajectory, or the onboard thrusters. It's not known at this time. The booster then was coming in far too fast. They tried to relight the engines in preparation for braking for a splashdown, but the engines failed to relight. Some of them lit briefly and then went out again. And the booster then broke up in the atmosphere at about 500 meters altitude. Meanwhile, the tests that were planned were carried out. The first test was to open and close the cargo bay door on the Starship. This is the cargo bay door that will dispense Starlink satellites when it comes into service. So this was the first test of the cargo bay door. It did open and close, but there were a few problems. It seemed to be a bit stiff and didn't move smoothly. So not an unqualified success, but they did manage to close it. The Starship then performed a fuel transfer test where they transferred fuel from the header tank in the nose of Starship, which provides the fuel for the landing burn, to the main fuel tank and back again. And apparently that was successful. So this is very important because this will be needed. This fuel transfer will be needed to happen between 2 Starship vehicles in orbit to fuel the lunar Starship when it goes to the moon to dock with the Orion spacecraft and land people back on the moon as part of NASA's Project Artemis. So obviously there were no 2 vehicles here to transfer fuel between, but they wanted to see if they could move fuel about in microgravity, which has never really been tried before, and apparently they managed to do it. So that was good. Then the Starship lost, as we saw, started rolling uncontrollably, lost the attitude control, started its re-entry over the Indian Ocean. As you saw in the video briefly, the Starship began to glow from the heat and that lovely bright plasma surrounding the vehicle, but the re-entry was too fast. And then Starship lost contact with both the ground station and the Starlink satellites that it was transmitting to. And then it broke up at around 54 kilometers altitude. Now, okay, so it wasn't a total success. So what were the successes of this flight? First of all, this was the biggest spaceship ever to achieve orbit. And I've put an asterisk there because, as I said earlier, it was never meant to achieve orbit. But if they had fired the engine for just a few seconds more on the ascent, they would have put it in orbit. So it was capable of being in orbit and almost certainly would have made orbit had that been the plan. But it was the biggest spaceship ever to do this. Biggest, heaviest, most massive spaceship ever to do this. So that was a first. The hot staging and the Starship separation worked perfectly. The cargo bay door opening and closing probably succeeded, although we don't know the fine detail of that yet, but it appeared to have a few problems. But as I said, they did manage to close the cargo bay door. The fuel transfer operation succeeded. The Starship got further into space than on any previous test by a long way because it flew around the Earth for nearly 40 minutes. So that was really good news. And SpaceX, by carrying out this flight, have demonstrated that they do have a launch system capable of deploying up to about 150 tons of payload. So this was another first. And they managed to transmit 4K video and telemetry well into re-entry. As you saw, even though the vehicle was surrounded by plasma on the way down, due to the heating from the atmosphere, they were managing to get a signal back via the Starlink satellites. And no spaceship has ever managed to transmit that far into the re-entry procedure. As if you remember the golden days of Apollo, there was always a communications blackout during the re-entry phase because the spaceship couldn't transmit through that plasma. But with Starship, it leaves a wake behind it because it's so big, and the signals managed to get out through that wake. So we had lovely 4K video well into the re-entry, which was absolutely amazing. The failures, well, obviously both ships were again lost. They both lost attitude control because of problems with their thrusters, and in the case of the booster, possibly the grid fins as well. There was damage to the launch mount after the launch, like there have been on the previous 2 test flights, but this time the damage was a lot more superficial, and I forget how much it was. It was a lot of steel that they sheathed the launch mount in to take the brunt of the incredible power of those 33 Raptor engines. That steel survived, although it's looking a little worse for wear. But the damage is superficial and nothing that they won't be able to mend in a couple of weeks. This is why they're building another launch tower at Boca Chica, so that after one flight they can work on any damage to the launch mount and the launch tower while launching from the other tower. So this is why they're building a second one at the moment. So there we are then. That's what happened during the flight of IFT3. Any thoughts, guys?
As you said, they didn't fire relight the Raptor engine while it was actually in space, and it did actually cross the Kármán line.
Yes,
even though it was at a slower rate. It was only for a short period of time, so it did actually make space itself. So that was sort of another achievement. And of course, one of the other, as you did mention, one of the other reasons why they didn't get it up to full speed, which I think is about 28,000 something or other kilometers an hour or something, or whatever it is, to go into orbit and stay in orbit, was because they weren't doing a full orbit. They were going to the Indian Ocean.
That's right.
This flight was scheduled to be a lot shorter because it wasn't even doing going all the way to Hawaii.
Yeah.
So that was one of the other reasons why they didn't get it up to full speed, because they knew they'd have to bring it down. As you said, they were a bit concerned. I think the main concern will be the rotisserie motion that it started to do.
Yeah.
Yes.
There was speculation whether it was doing what they call the barbecue, which is where other spacecraft are rotated just to keep the heat evenly spread across the actual body of the spacecraft itself. But that wasn't supposed to have happened, according to SpaceX. But that's one of the things they have got to sort out. As regards the booster, the main concerns they got to sort out is one, the engines didn't relight. When they've refired them to relight it to break it, only 3 lit, but 2 of them only lit for a very, very short fraction of a second, and then the third one went out. But as regards it losing control, everything seemed to be okay until it passed through the cloud layer, and I'm wondering whether or not there was possibly some wind shear or something that may have caught it.
Well, it's funny you should say that, because I was watching somebody talking about it today, and they said not only was there wind shear, there were wind shears in opposite directions, but layers on the way down.
Yeah, because I mean, what you showed was speeded up, but even in real time, the one thing that you could see was really trying to struggle to keep the attitude control, keep it upright and all that. But there was more successes than there was failures. Did you want to say something, Michael?
Yeah, I was thinking a couple of things actually. first of all, is the quality of the video feed. Absolutely amazing picture. Where the rocket flew through the cloud layer on the way up and on
the way down, yeah.
Those pictures absolutely amazing.
Stunning.
The other thing I was picked up on is what you said about the plasma wake with re-entry. I didn't realise what was happening. They were talking about that. So do you think the communications will be much better with Starlink than previous re-entries?
Well,
yes,
yeah,
definitely.
I think so. Yeah.
Yeah.
I mean, Starlink's already made a big difference. If you remember what the video from the drone ships when the Falcon first stage lands, they always used to lose the signal.
Yeah.
Because basically the rocking motion of the drone ship taking the exhaust from the rocket was causing the beam to miss the satellite they were transmitting.
Yeah, but I was thinking that this plasma wake, obviously that's caused by the sheer size of the ship.
That's right.
Yeah, and so that will create a window, if you like, for the communications to get through. I take it.
Yeah,
exactly.
Yeah.
And it's only able to do that because of the sheer size of the vehicles.
Yeah.
So the smaller vehicles, you would get away, but it would be tiny.
Yeah, they're still going to get the blackout for the ordinary capsules, aren't they?
Yeah. Because the receivers and the transmitters for the Starlink were actually on what we call the shiny side. So of course that's the side that's on top, and of course, because of the roll-in started so early, they kept getting transmission blackout.
Right.
And they had to wait to get the signal back so they could produce. But as you said, the pictures were absolutely fantastic, and in real time. That was the thing, because we have seen the plasma thing before with the space shuttle. They put a camera on a camera pod on the tail wing, and but that was shown in retrospect after the event had actually happened, only recorded. But to actually see when it came down, you slowly saw the grid fin in front of it, because the camera was mounted on the rear grid fin, the front grid fin, and we were looking back towards the engine bay. So we're looking at the grid fin at the bottom. When it started just to slightly glow, and then it got slowly changed color, and then it got brighter and brighter and brighter. And then when it actually did gain control for a while, you could see the brilliant glow of the plasma flying up through
it was amazing.
Through the air, and it was absolutely fantastic.
But
then of course,
any thoughts, Keith?
Well, obviously if it starts rolling, I did notice, I don't know the spacecraft all that well, but I could see that the heat tiles are all on one side.
Yes.
It's got to be the underside. And if
absolutely.
And it's cooking the bits that you don't want to cook. So that would, of course, the breakup, I expect. The other thing, though, is that, so we're talking about wind shear. It had to be pretty terrific if it's 150 tons and streamlined.
Yeah, absolutely.
But there you go. I mean, weather things like that do happen.
They do. And the other thing, Keith, about the heat shield was that only a few tiles were lost off the heat shield. So they certainly have improved the adhesion process of the tiles. There was a stage where you could see debris flying away from the Starship. And I think what that was, again, details are scarce to come by at the moment because obviously they're investigating. But it looks like one of the thrusters fired and knocked some of the tiles off, and that was the debris flying away from Starship. Just a couple of tiles, but it was clearly visible. But I'm sure they'll nail that. I'm sure they'll perfect that.
I mean,
even just 54 kilometers above the ground, which is when it broke up, the heat shield was still intact. And this is a really good omen for the future. They seem to have got the heat shield worked out. So, the
number of tiles lost is clearly a lot lower than they used to get on shuttle missions, which were notorious for shedding tiles, as you know. I did mention, I did mention, didn't I, that when I was over at NASA, they showed me the underside of Columbia. And you could see from the different colours of the tiles, which ones have been replaced, because brand fresh new ones were black and the older ones were grey. And the other thing was that stuff between them, the joints between the tiles, was fire rope, identical in every respect to what's in my wood burning stove at home.
Really?
Very good.
Yeah, I did wonder what they filled the cracks with, because you're always going to have a small gap, so you'd have to put something in there.
Yeah.
And of course, and I think it's not so much with Starship. They have got some tiles that are specifically cut, but with the shuttle, virtually every tile was a different shape.
That's right.
So they all had to be individually made and individually fitted, like
That's
with the
what told
Starship.
me. Yeah.
Yeah, and but every space shuttle did have some sort of strike for every launch. If it wasn't a bit of tile coming off, it was foam off of the main tank.
Yeah,
and of course, we know what happened with Columbia with that. We won't go into that.
Yeah.
But yeah, it was every single shuttle had a strike of some degree. Some serious, some not so serious.
Yeah. Incidentally, the foam on the tank you mentioned on the shuttle, again, a domestic point, it appeared to me to be identical to the stuff you have on hot water cylinders.
That's what I always thought.
The interesting thing is that as manufactured, it's yellow, but sitting out in the sun in Florida, it turns brown. We saw a fresh tank that had just been delivered and thought, well, that's odd. The colour's changed. And they said, no. They said they're yellow when they arrive and they're brown when they take off.
Yeah.
Oh, and one more thing. If you look at the very early shuttle missions, they painted the tank.
Yes, that's right.
They did, didn't they? Yes.
When they stopped painting the tank, they say quite a lot of unnecessary weight. And I heard a figure which I find hard to believe, that someone said that the amount of paint that they didn't put on was 4 tons. But I don't believe that. It seems too much to me.
4 tons? The paint's alarming.
And
so how thick was it?
That's saved a lot of time and money as well.
Well, yeah, of course. But yeah, we've gone back to the Starship. I think it was an absolutely brilliant affair.
Yeah.
I'm not convinced about the payload door.
No.
Because you did see that there was what was cool is that they showed pictures inside before they opened it, and there was all this sort of like fog floating around because it still had atmosphere in it. And as soon as they opened it and a crack appeared, it all got sucked out.
Yeah.
And that was really cool to see.
Yeah.
But when they were closing it, there was a period when it was moving quite nicely, and then it seemed to stick, and then it gave way.
Yeah.
And whether or not it got hooked on something or something happened, either way, it did actually drop. You see the gap reappear in a big drop. And they did say they did close it, but was it sealed? Which again would be a problem if on re-entry.
Yeah. Alan says brilliant third flight, definite improvement each time. It was. So, you've seen, we always see this with the media. They love disaster. They love mistakes and errors and problems, because that's what sells column inches. So, the number of articles I've said, Starship fails again. And it was a great success. This is a development program. Don't forget that it's only just a few years since the Starship existed at all. And they have moved on this faster than any rocket development program in history. If you compare that with NASA's SLS, the vehicle that is going to take people to the moon, the Space Launch System, which has been in development since what year, Michael?
Oh, my God. Now you're asking.
2012, something like that, would it be?
It's 10 years plus, isn't it?
Yeah.
I mean, Orion started during the development during the Constellation program.
Yes.
And that was the only bit of the Constellation program that was kept.
The tower.
Oh, the tower. Okay, the tower.
Yeah, the tower that they hacked about and butchered to make the SLS fit, and it actually leans and it's twisted. So,
Nice. Yeah.
And they blew the bloody doors off.
Yeah.
Comparing that with Starship now, what they've done with Starship, SpaceX have done with Starship in the last 3 to 4 years is just incredible compared in comparison.
It's incredible compared to any other rocket project ever.
Yeah.
You know, they've gone from nothing to last week's flight, which, you know, was 80% successful. And, you know, it's the biggest rocket ever built. And it's just mind blowing what they've managed to achieve. And I know, you know, whatever you think of Elon Musk, and God knows people seem to have some very strong opinions about Elon Musk, but whatever you think of him, he's an absolute genius with this engineering stuff. And you know, it's absolutely amazing. Anyway, viewers, what did you think of the flight? Did you watch it? Did you watch it on Space Oddities? We hope you did. And
we had quite a good viewing figure for that.
Any thoughts or comments, please put them in the chat.
Yeah, we had some good viewing figures for that. So, but of course, one thing I did mention is, and I couldn't remember exactly what it was, they were looking at flying on the 14th because it was an anniversary. It was their 22nd birthday.
That's right. That's right.
As it turns out. So of course, they're probably just a little bit older than the Orion spacecraft itself and the development of so.
That's true.
Yeah, it's really they've, as you said, they've come a very, very long way, very
and
very
they're
quickly.
actually a younger company by 2 years than Blue Origin. And if we just talk about Blue Origin's achievements in space. Right, moving on.
Yeah, we'll move on. Short and sweet.
Yeah, okay. Anyway, but before we go any further, just let me put this back on the screen for the moment, because I've got a little bit of an announcement here. 1 second. Just give me a second to get myself together here. Hang on, just give me a second. I'm all over the place tonight.
Well, while you're doing that, Andy, there were just a couple of other things because both ships were lost. The FAA have had to open up to investigate investigation again.
Yes.
So that could end up delaying the next flight. But I mean, because everybody was thinking, it's going to be sort of like possibly in a month's time, which it could still be in theory. But SpaceX, that when they issued the license, there was talk about that they have been given permission, not absolute permission, not license, but to fly 10 times out of Boca Chica.
Yes, that's right.
There were 5 that are re-entry jobs, and there are 5 that are not.
Really?
Yeah, so they think that. Do you know when we see some of the starships, they got no fins on them? They think that they may be used for basically getting into orbit and doing test things like refueling in space because they won't be coming back. Because there was 5 returns and 5. There was another word they used. I can't think what it was now. So they're thinking about they will be using 5 launches where the starships won't be coming back.
Yeah.
Not as a re-entry.
That would be S-26. That's the one without the heat shield or the flaps.
Yeah. So they'll be able to knock those up a lot quicker.
Anyway, there's no reason now why SpaceX can't do IFT4. Maybe in May. That's what people are saying.
Well, the thing is, they sorry to jump in there. That was something else I was going to say. They've brought out. I can't remember what they were actually talking about, but it moves it into April or mid-April. There was something that they came up with, and it was something to do with a license. It was something to do with communications, ground communications, and with it, they had to apply for a license for the ground communications, but that doesn't start until April
right,
whatever it was. But it's either the beginning of April or mid-April, so that could push it back a little bit further. But the more time they've got, the more they can actually do and make sure things are right.
I mean, what you have to remember is that although in terms of time it's doable, of course, what they have to do is to work out what the problems were and devise and invent fixes for the problems, which could take X amount of time. We don't know. One of my main concerns is that the booster engines didn't relight, again, because of a fuel sloshing problem inside the tank. So the fuel supply is still a problem when when the booster is descending. We've said there was strong wind shear and whatever, which was buffeting it, which could well have affected the fuel supply to the engines. But all of these problems that they had, they're going to need to devise fixes for. But technically, the FAA investigation shouldn't take that long this time, because don't forget, it's SpaceX who lead it. The SpaceX, tell the FAA what the problems were and tell them what the solutions are. So we'll have to wait and see. But it could be May, June time for IFT4. Anyway, let's move on.
Just one thing, just one more about the booster. It didn't do the fiery re-entry that Falcon 9 does.
No.
So when it came back through, it didn't have a sort of like the heat shield, fighting fire with fire thing, heat shield. The only time they were going to relight the boosters was to do braking when it was already in the atmosphere. So maybe some damage was caused when it coming back through. I mean, it wasn't coming through from space.
No,
but maybe there was some friction there. Anyway, we're speculating.
There we are. All right. So just an event, viewers. This is Manchester Astronomical Society have got an event on the 21st of March in a couple of days. And this is a talk called Jupiter and the Trojan Wars, being given by Professor Colin Steele of the University of Manchester. And the lecture will be held in the Schuster Building at Manchester University, Oxford Road, Manchester, in the Blackett Lecture Theatre on the ground floor. The lecture is free. Sounds really interesting. It starts at 7:30 UK time and will finish by about 9:15. So if you would like to go and see a really interesting talk at the University of Manchester, that's happening on the 21st, which is in 2 days' time. So that's on Thursday at 7:30 at the Schuster Building at Manchester University. So there we are. So I just thought I'd mention that, and there we are. Right, we're going to move on now. And Keith, are you okay there? Because I
think so. I'll just see if I can start the.
Because I don't see your presentation loaded.
Oh, it was earlier.
It seems to have disappeared. Okay.
Yeah,
we'll just let you try and sort that out while we move on. Next week on Space Oddities, we're delighted to welcome back a friend of Space Oddities, Dave Saras. And Dave has been attending the Winter Star Party in Florida, and he's going to be giving a report all about that next week here on Space Oddities. So we're looking forward to that. And we've got some other stuff lined up over the next couple of weeks for you. Right, I can now see it, Keith. So so there we are. Are you ready to start, sir?
Yeah, I reckon so. Yeah.
All right. In time-honoured tradition, I'm going to say, take it away, Keith.
Thank you. Right, folks, we come to part 4 of Measuring the Universe. And today I'm going to talk about what are known as standard candles. We're going to show you how we measure distance using the luminosity of stars. Once we know how luminous they really are, it'll make sense as we go along, I'm sure. Bear with me. Right. Okay. First of all, I should refer to something called the distance ladder. Now, we've been venturing into this from the start, but I haven't said an awful lot about it. But you can measure distances in space by a whole load of techniques. And basically, they're used to calibrate each other, or rather, to be more precise, the nearer techniques are then used to calibrate the next technique, which is then used to calibrate the one beyond that, and so on and so forth. So as we move from left to right in the diagram, each one of these methods allows us to validate the next one. But as you can appreciate, errors grow as we go from left to right. So, of course, as we go further and further into the universe, our grasp on exact distances gets more and more hazy. Nonetheless, though, we're making a decent go at it. So obviously, on the left there, we talked about distances in the solar system. They've just shown one technique in the diagram here, which is radar. And then the next one is, of course, stellar parallax, which we did last time. And it says there that the limit of the range of that is 100 light years. But of course, this is a very out-of-date diagram. And now with Gaia, we can reach out to getting on for 30,000 light years. So that's the parallax method. Well, after that, we're on to sort of luminosity-based techniques, with one exception, well, two actually, the Tully-Fisher relation, which you'll see on the extreme right there, and cosmological redshift, which is also on the right there. But looking at the others you see there, main sequence fitting, CFID variables, and type 1a supernovae, these all rely on us knowing the luminosity of stars and then comparing that to the luminosity we actually see in the night sky when we're a long way away from them. Okay, so basically, if we move on to the next one, we have to start by talking about stellar magnitudes. Now, most of you will be familiar with this concept. And basically, it dates back actually to ancient Greece. Hipparchus put together a star atlas, if you like, a list of stars in the night sky. And Ptolemy came along afterwards and tried to assign brightnesses to them. Now, although they didn't know it, we now know actually that the human eye actually detects a gradation in brightness from the brightest to the faintest stars that we can see in the sky, not withstanding light pollution, are of a factor of about 100. So a magnitude 6 star, which is on the borderline of being visible, is 100 times fainter than a magnitude 1 star. And thus, each step in the magnitudes between them, and there are 5 steps between 1 and 6, is in fact about 2.5 times brighter or fainter than the next magnitude along. So on the bottom of the diagram here, you can, of the slide rather, you can see a diagram that shows you where things sort of fit on the magnitude scale. And obviously, most stars are somewhere that we see anyway between 0 and 6, because although magnitude 1 was chosen by Ptolemy, he hadn't really realized that some of the stars are actually brighter than that. So Alpha Centauri, for example, is magnitude 0. Sirius, the brightest star in the sky, is actually brighter than that. So it actually has a negative magnitude. And the brighter an object is, the more negative that magnitude becomes. So going to the left, you can see Venus there is around about magnitude -4. The full moon, magnitude -12.5. And the sun, magnitude -27. Going to the right, though, we see a succession of stars of one sort or another, and then we get some idea with the diagram on the right of how faint an object we can see with some of the largest telescopes currently available. Clearly, this diagram predates the James Webb Space Telescope, which could see even fainter objects than we see on this diagram here. Now, the magnitude system looks a bit cockamamie, to be honest. Why don't we just go for absolute figures of luminosity? Well, the thing is, it's a log scale, and it permits us to compress very, very different brightnesses into a manageable scale. Because if we were to have things with their absolute brightnesses compared to each other, we'd be dealing with differences of millions, if not billions, between one and another. And that would make drawing graphs pretty difficult. So we need to consider 2 types of magnitude. Now, the apparent magnitude of an astronomical object, which is denoted by lowercase m, is the brightness of that object as we see it from the Earth. Simple as that. Now, this, of course, is going to be affected by 2 things: how bright the object really is, but also how far away it is. So a bright star like Sirius, which you see in the bottom right of the slide there, that's actually not as bright as, for example, the star Rigel, in Orion. But it appears brighter in the sky because it's much, much closer. Okay, now that gives us a problem then. We can't compare one star with another unless we've got some way of standardizing their brightnesses. We want to know what their intrinsic brightness is, in other words, how they would look if they were all the same distance away. So we have a thing called absolute magnitude, denoted by an uppercase M. And this is the brightness of a star measured at a standard distance of 10 parsecs, which is about 32.5 light years. And if we have all our stars at the same distance and compare their magnitudes, then we're actually seeing how they really compare to each other in brightness. Now, the link between the apparent magnitude that we see from Earth and the true, if you like, absolute magnitude of a star is given by a formula called the distance modulus, which is the formula you see at the bottom. Now, it looks pretty scary. It's got a log in it for a start. But the thing is, I don't want you to worry about that, because all we're going to do is just plug numbers in and use it as a tool rather than worry about exactly how it's derived and all the rest of it. Okay, now you'll see actually in that formula, though, that if we've got the magnitude and we've got the absolute magnitude, then we can deduce the third variable in that formula there, the distance, which is, of course, how we measure the distance to stars. Okay. So basically, we're interested in stars which have an absolute magnitude that we can predict. And there are 3 categories, possibly 4. I'll explain the 4th in a moment. Main sequence stars, which are stars in the normal phase of their life, which they spend about 85% of their life being main sequence. These are stars in which hydrogen is being fused into helium in their cores. The second type of star are Cepheid variables and RR Lyrae stars, which are variable stars. They vary in brightness with a period that's predictable. And these are post-main sequence stars. These are stars that are dying, basically. And finally, a third category is the type 1a supernova, which is a massive explosion, stellar explosion of extreme brightness. Now, I've just read this week, actually, that there is a 4th category now. Red giants and red supergiant stars obviously are quite bright and therefore would be useful as standard candles if we were able to measure their absolute magnitude with any reliability. Well, it turns out that some of them pulse in and out at a rate that is proportional to their, inversely proportional to their brightness in a similar way to Cepheid variables. So it seems we can use them as well. Well, I'm not saying any more about that now, though. It's hot news, as they say, and well, there we are. Right, okay, so let's move on to what main sequence stars are. Now, back in the late 19th, early 20th century, we had acquired by this stage a large amount of data about the stars that we see in the sky. A lot of this work was done with money provided by a chap called Henry Draper, and the people who did the work were a team of women known as the Harvard Computers. And basically, they got the spectra and all sorts of other information about a huge number of stars, which they put into something called the Henry Draper catalogue. Now, if you've ever looked at star designators in star charts, you may have seen occasionally a star marked HD followed by a 5-figure number. That will be a Henry Draper catalogue star. Now, the thing is, if you've got lots of stars, it occurred to 2 people, quite independently of each other as it happened, to plot them onto some sort of graph. One was an American by the name of Russell, and the other was a Dane by the name of Hertzsprung. And the diagram that they came up with is known as the Hertzsprung-Russell diagram, or HR diagram for short. Now, basically, the bottom of the graph, the x-axis, if you like, is a reverse plot of temperature. So the hottest stars are on the left-hand side, and the coolest stars are on the right. The thing about stars is that, contrary to hot and cold taps at home, The blue ones are the hot ones, and the red ones are the less high temperature ones. Now, up the left-hand side on the vertical scale is a logarithmic luminosity scale. And to give you some idea of the difference between the very brightest stars at the top and the bottom, there's a difference there of 10 to the power of 11. So that's, you know, just trying to work it out actually, there's 100 billion times difference in brightness. So the little red dwarfs down the bottom right there are pretty dim, and then obviously these bigger stars, hotter stars, top left, are much, much brighter. Now the main sequence is that line that runs down, that sweeps down the middle there, and it did surprise Hertzsprung and Russell that in fact actually that the stars did plot the way they did. They expected to come up with a random result, and they didn't. Basically, what it told us was that the hotter a star is, the brighter it shines. And that's what you see in the graph there. There are other groups in there, by the way. You can see the giants, the supergiants, and the white dwarfs. Well, we'll ignore those because we're going to focus on the main sequence. Bottom left of the slide, you'll see there's a graph there that shows you how the luminosity of a star varies with its temperature. So you can see several lines there, 2000, 3000, 4000, and 5000 Kelvin. And you can see how the graph line goes up very sharply. Because in fact, the luminosity of a star per square meter of its surface is proportional to the 4th power of the temperature. So, by the way, by temperature, I mean the surface temperature. So a star that is 2 times hotter shines 16 times brighter. Okay, so we got some idea now of the brightnesses of stars. So obviously we can measure the apparent magnitude of a star. We can determine its absolute magnitude from its position on the Hertzsprung-Russell diagram, and away we go. There's one thing that causes a problem though, and that is that, for example, if we look on the right-hand side, we can see some red giants and we can see some red dwarfs, and they have the same temperature. So how do we tell them apart? Well, the answer is that the spectra of these stars, when examined more closely, are different. Sorry, I'm wondering why my slide won't change, but I'm going to try again. Hang on. Let's try that instead. Bear with me, folks. There we go. Oh, no, gone one too far. That one. Now, if you look on the left-hand side there, these are close-ups of spectra of some stars, all of the same temperature. They all have a catalogue, a designation of F. You'll notice on the bottom of the graph there on the right, you'll see F is about 2/3 of the way to the right there. These are stars that are essentially yellow-white. And the top line is for a giant star in that category. The middle line is for a main sequence star in that, a subgiant in that category. And finally, the line at the bottom is for a main sequence star in that category. And if you look carefully at the spectral lines, you'll notice that the giant stars have spectral lines which are narrower than the main sequence star. And I'll draw your attention particularly to the hydrogen delta and hydrogen gamma lines, which are marked on the bottom spectrum there. And you'll see that if you look at those same lines further up, you can see they get narrower and narrower. Now, the reason for this, actually, I won't go into huge detail, but the stars in the main sequence have denser atmospheres than the giant stars. And so the atoms in the outer atmosphere are interacting with each other more than they do in a giant star's atmosphere, where they're more spread out. Hence, the spectral lines fuzz out. And that's basically what you're seeing here. Now, I know that people are going to say, hang on a minute, I haven't got a clue what he's talking about here. I have got to talk about how stars work, by the way, and if we come back to that sometime, you'll see exactly how all that works. Point is, and this is the main point, we can tell the difference between a main sequence star and a giant star, even though they're the same color and therefore the same temperature. Of course, the better our HR diagram is, if we're going to use for measuring distance, the more accurate our results are going to be. So we've calibrated our HR diagram by gathering up data for stars we know the distance of using parallax. In other words, this is an example of using one method to validate another. And by using parallax, Hipparchus, which was the predecessor of Gaia, constructed this Hertzsprung-Russell diagram that shows you the main sequence and the giants up to the upper right and the white dwarfs down, not very many of them, I might add, down to the bottom left. Okay, so how do we actually do this? Well, basically what we do is if we can measure the temperature of a star from its color, then we can start with that temperature on the bottom axis of the Hertzsprung-Russell diagram, project up to the main sequence line, and then project across to the left to find what the absolute magnitude of that star is. So, for example, here I've marked out a star which has a temperature of 7,500 degrees at its surface, and the absolute magnitude plots at around about +1 on the magnitude scale on the left-hand side of the graph there. So we can tell from the temperature what the absolute magnitude of a star is. And of course, we've got the apparent magnitude. And if we've got those two bits of data, we can then put them together to find the distance. But in fact, actually, astronomers look at the color in a more sophisticated way. What they do is they image the star with different filters and look at the differences in brightness as viewed through different filters. And the color index of a star is what it is called. And in fact, this is the difference between the star in the blue filter, how it looks, compared to how the star looks through a filter that's more or less in the middle of the visible range, which will be a sort of greenish color. And as you can see on the left-hand column of that chart there, the hot star at the top there has a negative color index because, of course, it's got a lot of blue compared to the visible. Whereas down the bottom, that reddish star, the M0V star down the bottom there, it's got a positive color index because there's more visible light than there is blue in it. Okay, so that's what we do. We measure the color index. That gives us the temperature, and the temperature then allows us to work out the intrinsic brightness, the absolute magnitude. Here, for example, is another Hertzsprung-Russell diagram in which I've taken the data from the second star down in the previous table. And you can see I've taken an arrow up to the line, the main sequence line, and then taken it across to the left there to show the absolute magnitude. And minus 6.7, I've got to tell you, is a pretty damn bright star, which it would be because it's a bluish colored star and therefore very hot. Okay, so here's an example, a worked example, if you like. We're going to look at Theta Orionis C, which is just below the Orion Nebula. It's got a color index of just a little greater than 0.02, and an apparent magnitude, that's the brightness as seen from Earth, of about 5. That's +5, of course. And we can find the absolute magnitude by taking our arrow up from the bottom there, from 0.02 up to the main sequence and across to the left to give us an absolute magnitude. And that absolute magnitude appears to be around about 0.08. So we feed those numbers into the formula, the distance modulus, and out comes the answer of 73 parsecs. Now, actually, this star, of course, is well within the parallax range of Gaia and etc. But it's just a worked example to show you how it works. And that's basically it. Now, somebody by now will be saying, hang on a minute. The main sequence isn't a thin line. It's kind of like a huge fuzzy smudge. Therefore, getting an exact position, do we take the middle of the fuzz, or do we take the right-hand upper side or the lower left-hand side? Good question. And that, of course, introduces some uncertainty into our calculations. nonetheless, we got a working figure. Now, if you want to look further out into space, you need brighter stars. And there's two categories of post-main sequence stars that are very bright indeed. They're 10 to 100,000 times brighter than your average star. And so they can be seen a long, long way away. And these are the Cepheid and RR Lyrae stars. Now, they swell up and they contract. And the reason why they do this is because the helium in their outer atmospheres becomes doubly ionized. That is, the helium atoms lose both their electrons as they heat up. And when they do that, they become opaque to the starlight. In other words, they block the starlight in of the star. And that causes the star to swell up. And when it reaches a certain point of swelling, it cools down sufficiently for the helium atoms to regain their electrons to become effectively transparent transmitters of the light. And then the star shrinks again. And of course, as you'll appreciate, when the light starts coming through again, of course, the star gets brighter. So when the helium is opaque, the stars are dimmer. When the helium is transparent, so to speak, the stars are brighter. And they do this with a very regular beat. Unlike irregular variable stars, which oscillate all over the place and you can never predict quite what they're going to do next, these stars, you can set your watch by them. So that's great. Now, the thing is that the person who discovered all this, or rather realized the importance of it, was a lady by the name of Henrietta Leavitt. Henrietta Leavitt was one of the Harvard computers, and you see her there on the right. And what she realized was that the luminosity of the star was linked to the rate of the oscillating brightness. There was a period luminosity law. And basically, if you plotted these variable stars with brightness on the vertical axis and the period on the horizontal axis, you found that the brighter these stars were, the more slowly they brightened and faded. In other words, their period got longer. Now, during Henrietta's time, it was assumed that all these Cepheid stars were of the same sort. And in fact, you'll notice on this graph here, there are actually three categories there, two types of Cepheid and these RR Lyrae stars. Henrietta didn't know that. But nonetheless, the rule that she created, the period luminosity law, works brilliantly for type 1 Cepheids. So no problem. There's the formula there. Yes, there's a little log in it, but never mind, we can just use it as is. And the absolute magnitude of a Cepheid variable, m, is related to its period p by this formula. Okay, so basically, here we've got a picture of M31, which is the Andromeda Galaxy. And you can see there a blow-up of part of the galaxy showing you a Cepheid variable star. And you can see as you follow the vignettes from left to right, you'll see that it's getting brighter. And of course, a little while later, it will start to fade again, and then it will brighten again, and so on and so forth. Okay, so here's a few graphs of Cepheid variables. These are all in the galaxy M100. And you can see from the graph that the up and down oscillations are quite regular. All we got to do then is to measure the period of each Cepheid, and at the same time we can from the graph get the apparent magnitude, the brightness that they appear to be from Earth. So here's some lines. You can see the blue lines give us the period between the two blue lines, and the red line gives us the apparent magnitude. Now, the apparent magnitude marked with a little m on the left-hand side there, you'll notice that the scale is upside down. And the reason for that, of course, is that, as you know, as the stars get fainter, the positive magnitudes get larger in numbers. So a 26 magnitude star is fainter than a 24, for example. Okay, so we can make measurements on these graphs. And here are the measurements. I won't trouble you to do it yourself. And you can see the first one has a period of around about 54 days, and it has an apparent magnitude of just a tad under 25. And then you can see all the others there with their periods and their apparent magnitudes. We're just going to work a solution for one of them, by the way, not all 6. But basically, we're going to use the first one that we saw in the previous graphs there. So there's the formula. We put 54 in because this, by the way, works with days. And basically, we find that the absolute magnitude is minus 6.17. So this is a very bright star, but then we know that because Cepheid variables are very bright stars. So basically then, we could do it with a formula, but you might be interested to know, of course, you don't have to do it that way. You could just do it with a graph. Here's a graph here, and it shows you how you can take the period on the bottom line on the x-axis there at 54 and take it up to the blue line there and across, and you can see you're getting pretty much the right magnitude that way. So either way works, and basically you can use that period then to work out the absolute magnitude of the star. Great. Well, once you've got the absolute magnitude, and of course we've already measured the apparent magnitude from the graphs, we can feed all that into our distance modulus, which we saw before, and lo and behold, we find that this Cepheid variable is sitting in a galaxy that is 16.5 million parsecs away. And when you bear in mind that a parsec is 3.26 light years, then you've got to multiply that by 3.25. It's going to be about 50 million light years to that galaxy. So that shows you, therefore, how impressive Cepheids really are, that we can see them that far away and that we can measure distances to galaxies using those stars. And of course, the great thing is that when you look at a galaxy like M100, or indeed M31 we saw earlier, we're going to have a lot of Cepheids, not just one. So we can gather them all up, do the calculations on each and every one, and that gives us some way of working out the uncertainty in our overall value. Now, of course, that's fine, but the universe is very, very big. And so to get to objects that are even further away, we need to resort to an even brighter category of star. And we're going to look at the type 1A supernova. Now, supernovae, and this is a fault of a lot of school textbooks. Everyone thinks a supernova is always a large star that implodes on itself, and the outer layers explode outwards, and you're left with either a neutron star or a black hole or whatever. But actually, there's another category which is entirely different to the rest, which is a binary system of 2 stars. And they're a contact binary. They're quite close to each other. And one of the stars burns through its fuel much more quickly than the other and dies and becomes a white dwarf, which is a compact stellar remnant. And a white dwarf is typically about the size of the Earth, but it's very, very dense. A teaspoonful of white dwarf material would be around about 4 tons, to give you an idea of what we're talking about. Now, material from its neighbor can be gravitationally pulled off by the white dwarf and spins down onto the white dwarf surface, accreting on the surface. Now, what's happening now then is the white dwarf is gaining mass from this material that it is sucking off. Moreover, that material that it's taking off is mainly hydrogen. Eventually, the mass of the star reaches what's known as the Chandrasekhar limit, which is 1.38 times the mass of our sun. And when that happens, the white dwarf essentially implodes on itself, and the huge amount of energy involved in this ignites the hydrogen that surrounds it in a nuclear explosion. So you've got a big hydrogen bomb going off, basically. That's what you've got. So it's a thermonuclear explosion. And unlike the classic type 2 supernova that leaves a remnant behind, like a neutron star or a black hole, this completely destroys everything. Nothing is left. But here's the thing. If that explosion occurs at the Chandrasekhar limit, at 1.38 times the mass of the sun, every time, for every type 1a supernova, they'll have exactly the same brightness, which means we can use them as a standard candle. Well, before we look at that in more detail, I thought you might like to have a look at some supernovae. The diagram on the top right there shows you one exploding in a galaxy, NG 4526. The galaxy extends way beyond that thick dust cloud you can see there. You can just about make out the hazy background of stars, and you can see how bright that supernova is. It's actually outshining the core of its own galaxy. That gives you some idea of the amount of energy being released. And that is a type 1a supernova, so that would be a splendid thing to use for measuring the distance of that galaxy. And indeed, we're going to use it as a worked example in due course. The bottom picture there shows you a supernova which went off in 2012. It's down the bottom right of the diagram there, or the picture rather. That's M95, which is one of the galaxies in the constellation of Leo. And the little dot that you can see to the bottom right of the core of M95 is a supernova exploding. In other words, if you went out tonight and took the picture of the same galaxy, that dot wouldn't be there anymore because the explosion occurred 12 years ago. Here's the astonishing thing about this. I took this photograph with an ordinary camera, not with a huge telescope. This was just taken with a DSLR camera and a telephoto lens. That shows you just how bright these stars really are, that you can actually pick them up with elementary apparatus like that. In fact, the kit I used is what you see on the right here. That's not mine, funnily enough, but it is almost exactly like mine. That's a Nikon camera like mine with a similar lens to mine, and it's mounted on a thing called an Astrometry, which is an early model of a tracking device. That little thing on the left, by the way, is a polarscope for aligning it. And using the same kit, I took this picture in 2014. And this is this is an Ursa Major, and this is the Cigar Galaxy. You can see top left there, and going off in the Cigar Galaxy, lo and behold, a supernova, which I've blown it up a bit, and I've marked it with a red arrow, so you can actually see. Now again, if you look at that galaxy now, you'll find that dot's no longer there. And again, you can see how bright that is. I mean, it's actually outshining the core of its own galaxy. That gives you some idea of what we're talking about. By the way, I caught this picture literally 24 hours after it was discovered, because the discovery of this supernova is one of serendipity. Some undergraduate students were just using a telescope one night, making casual observations, and looked at M82 and thought, hang on a minute, what's that dot doing there? We've not seen that before. It was purely accidental that they found it. Of course, using modern synoptic survey telescopes and software, we can now hunt down supernovae systematically. But back then, only 10 years ago, a lot of them were still found almost by accident. Okay, so our supernova has a peak absolute magnitude of around about -19, which is very, very bright indeed. So we can pick them up a very, very long way away. Obviously, you have to study these supernovae for a time to watch them brighten and then fade again to find when the peak brightness has been reached. And then, of course, if you measure the apparent magnitude of the star at its peak brightness, knowing that its absolute magnitude is -19.3, we can put the data into our formula. And as I said, we're going to use that first supernova you saw. And you can see, basically, its magnitude as seen from Earth was +15.2. Its absolute magnitude -19.3. Put all that into the formula, and you come out with a staggering distance of nearly 8 times 7 parsecs. That's 80 million parsecs away, or somewhere in the order of 20. Hang on, we got that right. Yeah, 25 million light years. So you can use supernovae over vast distances, and in fact, we've been watching them all the way out to almost the edge of the visible universe, looking for them in galaxies much further away than this one. Now, in fact, there's just one fly in the ointment, and of course, you might understand that we are making an assumption that all Type 1a supernovae are identical and therefore can be used as standard candles. There are people out there who are a little doubtful about that. So obviously we're gathering more and more data to try and narrow things down a bit. But some might actually not be white dwarfs drawing material off a companion. There may be a binary system of white dwarfs that are colliding with each other. But of course, if you were listening last week, you'll know a lot more about gravitational waves than me. We can pick up binary systems in collision using gravitational waves. And of course, you'll get a different signature than you would to a classic Type 1a supernova. There's one more thing to add. I've not said anything about cosmology at this point, but of course, Type 1a supernovae were the subject of study by Saul Perlmutter and his team back in the late 1990s, when they discovered that they were the ones that were in galaxies much further away were dimmer than predicted. And it showed that, in fact, that the rate of expansion of the universe was changing with time, and it is, in fact, in the process of accelerating. But that's another story, and we'll leave it there.
Great, fantastic. Thank you very much, Keith. I mean, that's amazing. And you know, these white dwarfs detonating like that, they really are unbelievably powerful thermonuclear explosions. You know, this I'm guessing would be many times more violent than if we detonated every single nuclear weapon on the planet.
Oh yeah, you're not even close.
Not even close. No, amazing. So, I mean, with regards to the distance ladder, I mean, is the cosmic microwave background ever used for this?
Yes. Wait for the next episode.
Okay.
There's one more episode to go in which I'm going to look at techniques that are not based on luminosity. And I'm going to be looking at something called the Tully-Fisher relation, which shows how the rotation of spiral galaxies can be used to determine their mass, therefore their brightness. And the other thing, of course, is cosmological redshift. We can assess the distance of galaxies in the universe from the rate at which they're moving away from us. And obviously, the problem with that is getting an accurate determination of the Hubble constant, which until the early 90s, when the Hubble Space Telescope was launched, we really didn't have a terribly good handle on what the Hubble constant was. There were values floating around between 10 and 100. As it is now, it's just a bit under 70, and everyone pretty much agrees on it. But of course, it's a cross-calibration thing again. We've been able to use, the cosmic microwave background radiation as an independent confirmation of that value for the Hubble constant.
Sure. I've just done a quick calculation, and a star that is magnitude -19 is 3.7 times 10 to the 18 times brighter than the sun.
Yeah, that sounds pretty much. Yeah. I mean, what we're basically saying is one went off in our neighborhood of the galaxy, we're dead.
Yeah. Yes. Basically.
Yeah. End on a happy.
Yeah. Thanks for cheering our viewers up. But I mean, we are overdue for a bright supernova. Well, any supernova in our galaxy, aren't we?
Yes, we think there's probably about 3 a year. But because a lot of their galaxies are obscured by dust that we can't see, we don't see them, of course. And we haven't had one that we've observed in our own galaxy since the 17th century.
That's right. That's absolutely right. Yeah, so we're well overdue for a bright supernova. I wonder whether Betelgeuse will step up to the mark.
It will eventually, but when?
Eventually, yes.
Yeah. By the way, did you see that Betelgeuse is misbehaving again?
Yes.
Yeah.
Again, isn't it? Mm.
Yes, it's dimming again, and apparently we may have had its brightness wrong all along, because they think Betelgeuse has got such a turbulent atmosphere that that can affect our distance measurements. So Betelgeuse is a fascinating subject.
Yeah.
And,
I saw a description that said the surface is actually boiling.
yes,
And
that's
of course, this
right.
it's just very strange. I mean, we know ours is sort of like simmering when we see all the granulation come up to the surface and then sink down again. But this is actually boiling. It's it's going to spill over.
Because the earliest interferometer telescopes, that's groups of telescopes working together, like the very larger VLA in Chile, actually able to get resolution sufficient to pick out the surface details of the larger stars, like Betelgeuse. And in fact, one of the early images I saw, it had a huge blob of something coming up to the surface, right bang slap in the middle. So you're right, it's boiling over and, really quite irregular. There's another star called Monoceros B838. If anyone looks that up on the internet, you'll see it's surrounded by dust shells that have been blowing out and being lit up by light from the star at periodic intervals. So they are pretty chaotic. And of course, that's why we call them irregular variables.
Yeah, the one in Monoceros, apart from being anything else, it's beautiful. I mean, it's a beautiful object. It really, really is. Okay, well, listen, thanks a lot, Keith. And obviously, we would very much like you to do the last part of your absolutely amazing talk on astrometry. Perhaps we can arrange that, maybe not for next week, but maybe the week after if you're available.
Week after is fine, yeah.
Okay, so we'll look forward to that then.
Yeah,
so
it's already made. Got it ready.
Right, great. Final part of Keith's epic look at astrometry. I'm sure we've all learned a lot, and it's been really good. So thank you so much, Keith, for that. And skulking in via the back door while Keith was speaking was Roger. So how are you, Roger? Are you okay?
I'm fine.
Oh, good. Glad to hear it. Well, Thank you for joining us. You've been doing a talk, I understand.
Well, it's been a part of a three-way astronomical society meetup for over the last month, and that's between the Bath Astronomers, Bristol Astronomical Society, and Cardiff Astronomical Society.
Right.
And it's giving everyone a heads up on how the universe comes into being, how it works, the life and death of stars, and knowledge all about our solar system. And I did my little piece on astrophotography.
Yeah. And did it go well?
It seemed to have a lot of interest, and the associating astronomical societies seem to have picked up quite a few new members. So
that was
doing something right.
Yeah, absolutely true. Absolutely true. Okay, just one thing that occurred to me, Keith. You mentioned synoptic survey telescopes there. When the LSST or the Vera Rubin Observatory, as it's now known, comes online, I think is it next year or the year after next? Can't remember, but soon, astronomically speaking. I'm sure we'll be spotting a lot more of these supernovae, and a lot of other things, and including things we may not have known about up to now. The Vera Rubin Observatory is
Guy has been plotting quite a few supernovae.
Yes, that's right. But I'm so much looking forward to the Vera Rubin coming online. saw some recent photographs of the construction, and it looks nearly finished now. So so they're just ready to start putting the instruments in, including, of course, the world's biggest digital camera, the size of a car. And with, I can't remember, what was the resolution? Does anybody remember the resolution of that camera?
I can't remember.
No, it's a big boy, and just give me 1 second. I'm curious now. Just talk amongst yourself for a second, and I will look that up.
Yeah, while you're doing that, actually, I want to clarify something I didn't clarify earlier. Henrietta Leavitt's masterstroke in determining the period luminosity relationship was to look at Cepheid variables in the Magellanic Clouds, because they're all more or less at the same distance to us. So we could reliably look at their apparent magnitudes and know that they, were dictated by the stars' intrinsic brightness themselves, because distance wasn't a factor in the work she did.
Right. Okay, thank you for clarifying that. And I've just looked it up. The resolution of the camera on the Vera Rubin Observatory is 3,200 megapixels.
Yeah.
So that's an incredible camera. And
it will take 15-second exposures every 20 seconds.
Yeah, absolutely. And it's going to be an amazing instrument. I think at some point, perhaps fairly soon, I'll do a little bit of a presentation about some of these new observatories that are coming online over the next few years, because there are some amazing instruments under construction at the moment, including, of course, the world's biggest ever telescope, the European Extra Large Telescope down in Chile, and which I've talked about before. But I think the Vera Rubin is worth. Yeah. And what I was going to say, if we did let off all the nuclear bombs on the planet, we might finally get rid of Ed Sheeran. So that's
or even Joe Biden. No.
Some you'll know that the Orion design of spacecraft, which was postulated some years ago, which involved dropping nuclear bombs out the back of a spaceship, requires 25,000 nuclear warheads to get you to Proxima Centauri, which just happens to be exactly the right number of warheads we have on the planet at the moment. So there you go.
Good use for them. Yeah, absolutely. Make space voyages, not war. So there we are. All right. Well, I think we'll wrap things up for tonight. We'll hold the gallery and Roger Skynotes over to next week, if that's all right with you, Roger.
Absolutely.
Because time's getting on, so we'll leave that till next week. Don't forget, please do send in your images. Email them to spaceodditieslive@gmail.com. 1 image per email, please, and entitle your emails gallery entry, anything with the word gallery in, because that's what the software looks for. Yeah. And Daz's microphone has stopped working for the evening, which may be seen as a blessing in disguise for the rest of us. But anyway, Daz and Mike hopefully will be back next week. So anyway, from all of us at Space Oddities, thank you so much for your support. We do value you being here. We will be back next week. Don't forget, as I said, Dave Saras will be telling us all about the Winter Star Party in Florida next week, which looks an incredibly interesting event that he's just come back from. So we've got that to look forward to, and a few other things that we will no doubt schedule in the meantime. So from all of us at Space Oddities, have a fantastic week. Looking forward to Easter, as I'm sure everybody's looking forward to some time off next week, as I have. And but we will be here back Tuesday, 8 p.m. UK time, 3 p.m. EST next Tuesday. And until then, have a fantastic week. So from all of us here at Space Oddities, thank you for your support and good night.